So this is about the series combination of these conductors. And parallel combination we are going to discuss now. This is maintained at the T1 and next it is a T2 here. This is the one metal rod 1 here. This is another metal rod 2 here. That way, if n metal rods are connected, here T1 is greater than T2. Here, previously in the series combination, our assumption is length is different, area is same. Here our assumption is length is same and area maybe is different. If this is the temperature T1, is a temperature T2, if they are connected, rod 1 the heat direction flows like this, rod 2 the direction moves this side, and some nth rod it moves like this, final rod this one. If you are finding that heat current to the rod 1, I1 is equal, we know this temperature difference T1 minus T2 by R1. So R1 is the thermal resistance of the rod 1. What about this I2? Same temperature difference, rod 2 is also maintained the same temperature difference. So we are taking this T1 minus T2 by rod 2. So R1 is the thermal resistance of the metal rod 1, R2 is the thermal resistance of the metal rod 2. That way we are taking some nth rod T1 minus T2 by Rn. If we are taking this, total heat current flows from this rod to the other rod. So total I current is equal to I1 plus I2 plus In, because heat flows from this cross section, heat flows from this cross section, heat flows from this cross section. I want the total heat flow. This will be sum of this I1, I2 and In. If I add all of the things, T1 minus T2 by R1 plus T1 minus T2 by R2 and so on, T1 minus T2 by Rn. This can be, we can write down T1 minus T2 is taken common, 1 by R1 plus 1 by R2 plus 1 by Rn. This is the total current. So total current, for the total current also the temperatures differences, T1 one end is there, other end is T2. So T1 minus T2 by R effective. So R effective in parallel combination. This can be T1 minus T2 into 1 by R1, 1 by R2, 1 by so and so, 1 by Rn. If you cancel the things, so finally what you got is the total resistance, the parallel combination will be equal to 1 by R1 plus 1 by R2 and so on, 1 by Rn. If you observe this in the resistors, this is R1, this is connected parallel R2 and Rn here. So 1 by here also what we are getting, 1 by R2, 1 by R. So the same thing that can be applicable in the electricity also. This is that effective resistance in the parallel combination. Next, this conduction process is over. Next one, I am going to start this thermal radiation. Consider this is the body here. If the radiation comes, it's incident on this. Some radiation, this is the total initial radiation, let Q here. Some radiation, what happens that may reflects. Some radiation that may transmits, some radiation that can absorb. If you observe the diagram, Q is that incident radiation that can be splitting into 3 ways. That part of that energy that in the form of absorption, the part of the energy is transmission, that part of this is reflection. If you apply the conservation of energy, so incident energy Q here, R plus A plus T here. This is the amount of incident energy, this is the amount of reflected energy, this is the amount of absorbed energy, this is the amount of transmitted energy. If you are taking Q by Q, I am taking, this is about R by Q here, A by Q and T by Q. This can be 1 here. I am writing this R by Q is a small r plus this is a small a, this is a small t here. So, small r is the ratio of the amount of energy which is reflected to the incident energy. Small a is nothing but amount of absorbed energy to the incident energy. Small t is the amount of transmitted energy to the absorbed energy. So, this small r we can call it as reflectance. Small a is called absorptance and small t is the transmittance. So, these are the coefficients. If you observe this, let T is equal to 0. This is our assumption. That means the coefficient of transmission, that is transmittance, is equal to 0. If you apply this T value here, we are getting R plus A is equal to 1. From if R is more, A is less. If A is more, R is less. That means if the particular body, it will have more reflectance, this A value will be the less, if vice versa. If A is more, R is less. Hence, we can write down good reflector is a bad observer. This is our assumption 1. Another assumption we are going to discuss, I am taking the T is equal to 0. Again, this is another assumption. R is equal to 0. If I am writing T is equal to 0 and A is equal to 0, so here T is equal to 0 and R is equal to 0, A becomes the 1. What do you mean by A here? It is the ratio of this absorbed energy to the incident energy. That means if A is equal to 1, definitely capital A is equal to Q. If you observe this, whatever the energy is incident on this, that can be completely it absorbed. This is the body what we are going to discuss now, black body. So, the black body which absorbs the total radiation which is incident on this. In this case, the coefficient of transmittance and coefficient of absorptance has to be the 0. Generally, the black body we discussed at particular wavelength. So, we are taking right R lambda here, A lambda here, T lambda here. This is specific at lambda's values. After that, suppose if it is in one body here, the energy is incident on this. After particular some time, this body, what happens that is radiated per unit area we are taking and unit time. So, the factor that gives which is emitted, that gives as a emissive power. Whereas absorptive power we are taken as A lambda here. So, emissive power is defined at dq lambda which is emitted at particular wavelength here. Absorptive power which is absorbed ratio of this and to the incident. The relation between this emissive power and absorptive power is given by the Kirchhoff laws. At a particular given temperature, the ratio becomes is a constant. This can be what happens that emissive power of the black body, because for the black body A lambda will be equal to 1. This is about that Kirchhoff laws. If you have taken this E lambda, small letters corresponding to the ordinary bodies, capital letters corresponding to the black body, E lambda by capital E lambda is equal to A lambda here. So, this is the ratio of emissive power of the ordinary body to the emissive power of the black body will be equal to absorptive power of the ordinary body. this ratio what we are calling as emissivity. This is generally denoted by small e. So, emissivity is always equal to absorptive power of this body. We are using in Stefan's law. Suppose if it is a body here, consider it is a black body. The energy radiated at absolute temperature T here, the energy radiated or unit area is directly proportional to fourth power of its absolute temperature, E proportional to a to the power of 4, E is equal sigma a t to the power of 4. This is about for black body. If you are going for the ordinary bodies, what we are writing that E will be equal to sigma E a to the power of t to the power of 4. So, here emissivity of these ordinary bodies. This is about the black body which is maintained at the temperature T here. Let the same black body, if it is maintained at the surroundings, let this is a black body here and is maintained at some surroundings. This maintained at T here, this is about the T naught, then energy loss will be equal to sigma A t to the power of 4 minus T naught to the power of 4 here. This is for the black body here. For ordinary bodies, same sigma E A t to the power of 4 minus T naught to the power of 4. So, here emissive power E can be introduced for the ordinary bodies, whereas for the black body directly we are writing sigma E into t to the power of 4 minus T naught to the power of 4. So, this is about that radiation process, how the heat can be transferred for the black bodies. See here in the examinations point of view here, they are asking about that how the conduction takes place from one hot temperature to hot temperature in the both the combination, series combination as well as parallel combination. How can we get that effective K values in the both series combination, parallel combination? This is about that in the case of particular thermal conduction. In the radiation process, how the heat can be transferred by when it's maintained at the temperature T, and if it is a black body, how it radiates. If it is an ordinary body, it radiates. This is the way to prepare for this examinations. These points you majorly focus on these things.